Hi, my name is Gary Hawkins, and this video is about the demonstration of real-time photometry at a public outreach event. The event was the Julian StarFest, which took place in late August 2022. This is one of the main events that the San Diego Astronomy Association puts on each year as part of its public outreach series. The telescope used for this event was based around an 8-inch Celestron SCT. This was mounted on a Skywatcher EQ6R Pro mount. The optical chain behind the Schmidt-Cassegrain telescope consisted of an f6.3 focal reducer, a filter wheel with a UV-IR cut filter selected so that the light going to the imaging camera was constrained between approximately 400 to 700 nanometers. The imaging camera was a ZWO ASI 533MC. This is a 9 megapixel color CMOS camera. The OTA was also equipped with a guide scope. This would be important since I was planning to take 1-minute subs during the photometry. I started out with visual observing but quickly moved to electronically assisted astronomy. During the pandemic, many of you may have seen some of the live stream videos that I put together with my colleague Dave Decker and that can be found on my YouTube channel or on the SDAA YouTube channel. After the pandemic, I became more interested in undertaking photometry, and today that is my primary interest in astronomy. Photometry is the science of the measurement of light from an object, in this case stars. Looking up at the night sky, you might wonder, well, why is this of interest? Because the night sky looks relatively stable. However, that's not really the case. Many of the stars in the night sky are actually variable stars, and their light intensity changes over a period of days, weeks, or even years. There are also a number of variable stars whose light changes over a much shorter period, and it would be one of these stars that I would be looking at during this public outreach event. There are over 2 million known variable stars, so I had lots of targets to choose from. The variable star that I chose for this particular demonstration was V796Ceph. This is a 12th magnitude binary star in the constellation of Cepheus. For the 2 evenings during which I undertook measurements, the star started at the position shown by the big arrow and moved counterclockwise throughout the night to the position shown by the small arrow. I would be undertaking differential photometry for this event. Differential photometry is when we use one or more comparison stars to compare against our target star. Our target star is marked T1, and the 2 comparison stars that I chose are marked C2 and C3. These 2 comparison stars were identified by looking at an AAVSO finder chart for this region of the sky. These 2 stars were of similar magnitude and similar color to the target star. The reason we want to do differential photometry is that the comparison stars can be used to calibrate the target star. We can correct for the effects of air mass, and we can also correct for other systematic errors, such as the passing of high thin cloud through the field of view. The 2 main software programs that I would be using for this demonstration were SharpCat Pro and AIJ. SharpCat Pro was used for image acquisition and also the application in real time of dark and flat master files to correct for things such as hot pixels and dust bunnies within the optical chain. AIJ was used for real-time differential photometry and the display of the light curve. If you're familiar with AIJ, and in particular the CCD data processor window, you need to ensure that the M-plot is checked, and you need to ensure that the polling interval is set to something other than 0. What AIJ will do is look to a folder where it can find the images being acquired by SharpCap. Also within AIJ, on the multi-aperture measurements window, we need to ensure that the checkboxes of these three key parameters are set as shown in the slide. Since the real-time images collected by SharpCap Pro do not contain RA and DEC information, we would be using the centroiding function within AIJ to make sure that the photometry apertures stayed on the target and comparison stars as they drifted slowly across the image. With the technical stuff now in place, it was time to get ready for the public to attend the event. I was the last exhibit in the exhibitor area past the Celestron tent and the very impressive Woody Schlom Mobile Observatory. Even before it began to get dark, I had considerable interest in what I was doing. Since I collected data the night before, I was able to show those interested the formation of the previous night's light curve. As it got dark, my daughter helped me with the final preparations, and we discussed the finer points of sunspots on cookies. What you're looking at now is what the public saw on the second evening of the Julian StarFest. You can see the light curve for our target star forming, and this is speeded up by a factor of 60. Each one of the new additional data points represents a 1-minute photometric sub. You can clearly see the target star is exhibiting a completely different light curve from our two comparison stars. As you'd expect, our comparison stars are relatively flat, and our target star is in this case showing quite a sinusoidal pattern. If you look at the screen now, you can see the effect of a systematic error on both the light curve from the target star and the light curve from the comparison stars. What's actually happened here is our telescope has slewed past a set of power lines, and these have caused the light curve for both the target star and the comparison stars to dip. And since this systematic error affects both the target star and the comparison stars in the same way, the corrected light curve for the target star doesn't show this dip. The light curve for both the target star and the comparison stars continues to form. The variations that you see around the average value are associated with atmospheric scintillation. You can also see another curve on this diagram, and that is the slowly decaying black line. This is the air mass. What it shows you is that our target star and comparison stars are rising in the night sky. Since air mass is another systematic error, the fact that both the comparison stars and the target star are being affected in the same way allows for the correction of air mass within the corrected relative flux curve of the target star. This slide shows the measurement I captured not only for the 2 days that I was present at the Julian StarFest, that's the data points on the right hand side, but also for 3 other evenings where I collected a small amount of data from my home location. In the format this information is in at the moment, we cannot see the complete light curve, but we can get some idea of the shape of the light curve from this variable star. What we need to do in order to be able to see the complete light curve is to fold it, creating a phase plot. This next light curve, created by AIJ, shows the phased light curve for all of the data points collected over 5 nights of imaging. We can see that the light intensity varies in a roughly sinusoidal pattern with fairly similar maximum and minimum. So you may have been wondering what this light curve is. Well, it's the light curve of an over-contact eclipsing binary, and the curve is formed by the 2 stars rotating around a common center. In this situation, where both stars can be seen by the telescope, the light coming from our apparent single star is a combination of the light coming from the first star and the second star. When the smaller star goes behind the larger star, the light intensity drops because we can now obviously only see the light from the first star. When the star appears on the other side, the light intensity again becomes the light of the first star plus the second star. And as the second star transits in front of the small star, we will see a combination of the light from the smaller star plus the light coming from the outside of the larger star. When all this plays through, we get the light curve that I've just displayed. V796 has been discussed in a number of research papers, and from the research paper referenced in this slide, the following conclusions were drawn. This over-contact binary probably comes from a wide binary pair which has been subject to momentum loss and gravitational attraction. At some point in the future, the stars will come together with resulting envelope ejection. Both stars have similar surface temperatures and colors. These types of binary star are particularly useful as they can be used as distance markers throughout our own galaxy. The distance of this binary star has been calculated at 1,614 light years. One of the interesting things that we can do is to create what's called an OC plot. The plot you're looking at here is the observed period compared to the expected period. As you can see, there is a variation in this curve, and after I did the analysis on the data that I collected over these 5 days, my single data point for the OC plot falls well within the trend of the other data. What this plot tells us is that this is a binary star that probably has an unseen third component. I've mentioned the AAVSO several times. The AAVSO is an international non-profit organization for variable star observers whose mission is to enable anybody with an interest in photometry and variable stars to participate in citizen science. There are considerable benefits of membership. The AAVSO provides a series of comprehensive user guides. It provides extensive online tutoring through videos. There is access to the AAVSO VSX database and many tools for post-processing of data. And perhaps one of the greatest benefits of AAVSO membership is the ability to request a mentor. I am actually a mentor for the AAVSO, and currently I have 6 mentorees who are improving their photometric skills. Well, I hope you've enjoyed this presentation on photometric outreach. If you fancy giving it a try, I strongly recommend that you do. I was actually pleasantly surprised by just how the public reacted and how fascinated they were by the thought of 2 stars rotating around each other and the fact that we could actually observe this in real time. If you'd like to learn more about astronomy in the Southern California area, I strongly recommend you reach out to the San Diego Astronomy Association and look forward to seeing you again.